Traffic signal systems. In this presentation, we're going to be looking at an introduction to the system, their components, sensors and cameras, inductive loop sensors, signal lights, system operation, electrical service, system wiring, and finally, traffic signal training and certification. Traffic signal systems consist of many different components. The purpose of the system is to ensure safe and efficient vehicle movement through an intersection. Originally, the systems were timer-based, running through a set cycle of phases before repeating. This is an example of an old PCE 3000 controller. These older systems operated by means of a slowly turning dial which actuated cams when metal inserts were pushed against them. So here we can see a switch will move with a metal tab and then a metal tab located, that's determined by the installer. You could slot those in. It's very similar to what you'd expect to a standard 24-hour mechanical time clock today. The switch would then trigger the operation of a separate, larger drum motor. This drum had many layers of discs, each layer operating a separate light at the intersection. So each one of these brass-looking things, that would be controlling a separate light at the intersection. It might have been red, green, yellow, pedestrian, warning flashers, all sorts of stuff. As the drum rotated, different roller switches would then actuate based on the location of the cam inserts on the disc. So all of these, see these little cams? You would place those in different orientations to determine when this thing moved. It's crazy. So here's the system operating, and we can see it's got the metal tabs in here, and watch, it's going to actuate those levers. Here's a better one that's going to show the whole operation. Remember, those plastic black dials in the front that rotated, they control when this thing in the back turns. It's a monstrous mechanical behemoth. And there it is, twisting and turning, and all of those little micro switches getting moved. So some of the drawbacks from this type of system were there was lots of moving parts. High power consumption, friction and wear of moving parts, difficult to include site-specific inputs such as push buttons for pedestrian crossings or even sensors. Traffic signals are now operated by specially designed PLC systems known as controllers in this sector of the electrical trade. These controllers are built to a high level of quality by a limited number of manufacturers. And since these devices control the movement of traffic, any failure could result in loss of life. There are many ages of digital traffic signal controllers in use today. Each controller is programmed with the proprietary software of the respective manufacturer, much the same as what you would expect with any type of PLC in the electrical industry. Here's another type, a little bit older, and a McCain, much newer NEMA controller. Now, traffic signal systems are modular. This means there are separate modules for different functions of traffic, pedestrian, or obstruction warnings. Most components are plug and play. This means they come with a wiring harness and a plug for connection to the component. They're quick and easy to replace a faulty component. Cabinets are specifically designed for traffic controller applications. They are referred to as NEMA enclosures, which are set up identically from the manufacturer. Variations exist within the NEMA cabinet designs, typically based on the size of the intersection to be served. These variations are referred to as types, as in a NEMA Type 1 or a NEMA Type 2. Here's an example of the different apparatus inside the cabinet, and you can see the devices do not have field wires terminated to them or really any screw terminals. There are specially made wiring looms, which then terminate into a connector, which then connects to the module. And this allows for the very quick removal and replacement of this object here if it became damaged. All I have to do is disconnect 1, 2, 3 connectors and place the next one in place. Now, there is a typical layout for these types of cabinets, and here's a general example. There are many buses. So this one has bus 1 and bus 2, and therefore the connection of different types of flashers, load switches, and relays. The first object or piece of equipment is the traffic signal controller. A traffic signal controller is basically a PLC that has been specifically designed for traffic signal controls. It operates based on traffic phase program downloaded by the designer. It receives input signals from sensors, it sends output signals to lighting load switches or relays, and sometimes has an emergency personnel remote pendant for traffic signal override control during emergencies. The plug the controller itself is connected through plug connections only. No individual wiring terminates at the controller. And most traffic signal controllers operate with 24-volt DC signals only. So here's two additional types of controllers, and the one on the right has a removable pendant that an emergency personnel could use during a fare or during an emergency to control manually the lights within predetermined boundaries. The stages of vehicle movement within an intersection are referred to as phases. There are many industry, Department of Transportation, and provincial standards which determine how traffic phases are to be organized for every single situation. Traffic signal controllers are identified by the number of phases they can independently manage. The most common numbers are 4 and 8 phase units. Here's an example of a 4-phase controller controlling a 4 traffic phases. And this is just a basic sort of organization sheet. This is an example of an 8-phase controller controlling 7 traffic phases. And this is an example of the programming of an older Eagle type controller. And you can see here it's an 8-phase controller and it's a fairly basic interface. Of course, there are also connections that are available to computers. This is a more modern controller and you have all sorts of additional features and controls that can then be programmed in. Keep in mind, traffic signal systems are typically always active sites. This means it is unlikely the program can be trial run on the intersection without vehicles. There is no trial and error methodology here. Traffic signal systems can be thought of as a life safety system. If it fails or is incorrectly installed or programmed, lives will be lost. Lighting signal load switches. A load switch takes the 24-volt DC signal from the traffic controller and controls the 120-volt AC required for the lights at the traffic intersection. Basically, these are relays, specifically designed for traffic systems. Each unit is intended to control all 3 lights, red, yellow, and red, independently. It plugs into a receiver bus in the cabinet. And so it's got a number of connections for the 24-volt coming in and a number of connections for the 120 supply and out to the loads. Many of these switches have both an in and an out LED. When in is lit, that would mean that 24-volt DC signal is present from the controller. If out is lit, the 120-volt AC is energized going to the light. This can make for quick troubleshooting. If a light is not operating at an intersection, you can determine, is it the relay that's at fault, is it the controller, or is it a burnt out light bulb? And here's the back of it. You can see here it's meant to plug into a bus system in the cabinet. And so these are meant to be removed and inserted readily to be replaced if necessary. And here's the bus system. We can see a whole bunch of these and we have the red, yellow, green, and they have in and out on them. Here's another one where they're just all plugged in, and yet another. Conflict resolution or management modules. A malfunction management unit, or MMU, is a device used in a traffic controller assembly to accomplish the detection of and response to improper and conflicting signals and improper operating voltages in a controller assembly caused by malfunctions of the controller unit, load switches, or miswiring of the cabinet. Think of this as a fail-safe monitor. If it determines something is wrong, it will override the traffic signal controller and put all lights at the intersection into a flashing yellow or red. Proceed with caution. And remember, this is necessary because, well, vehicles are traveling at like 60 to 100 kilometers an hour. If for some reason the signals get screwed up, then there very likely could be loss of life. Now, how does that actually programmed in? Well, you'll notice on the far left-hand side of these units, there what appears to be a green line. And the way that these are programmed to determine when different signal lights can or cannot be illuminated together, as in the north and let's say the eastbound both going green at the same time, is with a card. Now, it's a very unique card. Let's see what it looks like. So here's someone shooting in on a disconnected MMU, and watch what he pulls out. This is a soldered card. So this is set up at the shop when the system is first being designed. And you'll notice it's all got numbers on it, and it then correlates to the load switches that are located in the bus down below. So all of those wired and soldered loops are meant to be placed permanently so that no one can inadvertently adjust the setting accidentally or maliciously. It's meant to be a fail-safe, so it is intentional that we solder a loop in showing these two cannot come on at the same time, and if they do, the MMU has to trigger into action immediately. On the left is a practice or test MMU card, and that's used when setting up a cabinet in a shop before the cabinet goes out for installation at the intersection. So you'll see it's a bunch of dip switches. Once they confirm that everything is all good to go, then they'll get the real permanent MMU card and they'll solder these loops onto the receiving outlets. A lighting signal flasher module. MMU modules require a separate independent means of operating the yellow or red flat lights in a consistent flashing operation. Flasher modules are used for this purpose. Flasher units contain an internal oscillator, I can't say that word, generator and relay. Flasher units operate 24/7. They only control lights when the MMU determines a problem. The MMU triggers a relay which transfers the input for each yellow or red light to the flasher unit. This causes a flashing yellow or red to occur on all tricolor signals, indicating proceed with caution to the driver. Regardless of what the traffic signal controller or load switch modules are doing, the light will be bypassed to the flasher unit. So here's an example of a flasher unit, and we can see here it's just showing it's oscillating on and off, plugs into a bus. And this is what the system would look like. Remember, the traffic signal controller takes 24-volt DC signals and it sends them to a load switch. Load switch is really just a glorified relay, and it's going to determine when the red, yellow, green need to go on or off. And that's then run through a 3-pole relay double throw. And so right now, the lights are all getting powered from the load switch. The flasher is right here, gets power in and then goes out. It's only wired up to this one here, that middle pole. And the middle pole on this particular traffic signal system is for the yellow light. And so right now, this is flashing on and off, right, on, I don't know, 1 second interval, something like that. The MMU controls the relay. When conflict is observed by the MMU, the relay is energized and the lights can then be wired for yellow or red flash. So let's say conflict is then noted by the MMU, it immediately energizes that relay. And notice now, the red and the green are disconnected from anything that the load switch is providing, and it doesn't matter what the traffic signal controller is seeing, and immediately yellow is on the interval flasher here, and it's flashing on and off. Now there can be a number of these relays depending on how many tricolor light pendants we have at an intersection. So here's a bunch of those relays. They're MMU controlled relays, and it really just depends on the system how many you have. Specialty sensor modules. Just like a PLC has separate cards for different operations, each sensor that is required to communicate with the main traffic signal controller must have an interface module. This module communicates with the sensor, then configures a suitable signal to communicate the information to the main traffic system controller. So we have things like inductive loop modules or sensors and radar and vehicle counting modules. So here's some examples of traffic sensor modules, and again, these ones look as though they plug into a bus system in the back, but often they're going to have wiring looms with connectors that then connect onto the front. And finally, modem connections. Traffic signal systems are often connected back to a larger control system which can be monitored or remotely controlled by the traffic management department of a municipality. And so the controls can be quite extensive with all sorts of different communication protocols, systems, and wires and cables, even fiber optic that then takes the signals back to a main traffic management center in larger municipalities like Calgary or Vancouver or Toronto. On the door itself of the traffic signal cabinet, there can often be door actuated switches, and these are used to automatically turn on the cabinet lights, but more importantly, alert the central traffic center that the controller door is open, because you don't really want people meddling in that thing. So let's take a look at a NEMA controller cabinet layout now with all the different items that we've sort of overviewed. Well, we've got the conflict management monitor. It usually hangs out beside the main traffic controller. And then we got a whole bunch of specialty sensor modules up above there. We then have the flasher unit, which is what is going to provide the on-off oscillating or interval flashing of the yellow in case there's a problem. We have all the load switches, which control the red, yellow, and green lights. And finally, CMU, or the conflict management monitor controlled relays. And those are the items that would be energized by the conflict management monitor. Finally, at the bottom, we have a bit of AC distribution because we need to have AC in order to drive all of the lights and all of the field terminations for the sensors, and the signal lights are down below, and those come up through underground conduits. Traffic signal controller cabinets are typically located near the intersection on either a concrete pad or mounted directly to one of the traffic pole lights. Enclosures must be weatherproof for obvious reasons. Since traffic signal controllers are typically municipally or provincially owned, the power supply cannot come from a local building. This means the service must be brought to the enclosure from either overhead or underground means. Many traffic signal enclosures will have separate compartments for the service and non-service wiring. So we can see here on the back of that, or side of that traffic signal cabinet, is a service entrance equipment and meter base. So we could have an overhead service, you could have an overhead that goes to a pole and then goes underground to the cabinet, or you could have a fully underground service. Some traffic signal enclosures are customized to also act as the service entrance. In these situations, there is a separate barrier to keep service conductors separate from all other conductors in the enclosure, and this is important and required as per Section 6 of the CC. So up here, that's the service entrance portion, and it's going to be barriered off. This is a single-phase 100 amp overhead service, and there are many different types of services that we can run into with different current values. This one's a single-phase 100 amp underground service, and you can see here, this is the location where the conductors come in, and it's all barriered off, and it then goes to individual single pole breakers. This is a single-phase 30 amp overhead service, and this one's actually coming from the pole of the traffic signal equipment that it is mounted to. And again, this one's a 3-phase 100 amp overhead service. So it really just depends on what the parameters are for the system and how large and how many lights you have at the intersection. UPS cabinets. Depending on the location and complexity of a traffic signal system, some signals may be required to continue operating even if main power is lost. This requires a UPS battery system specifically sized for the loads, and often this is a insulated cabinet that is separate from the main controller cabinet, off to the back of it, mounted to the back, something like that. It's got a bunch of batteries and a charge controller in it, and some form of a automatic transfer switch to provide power for this for a certain amount of time. There's an engineered drawing of one. So if we take a look at the overall AC, or 120 or 240, whatever it is coming in, we see the service panel goes into the UPS disconnect panel. It happens to be a 30 amp, and then it goes to, looks like it, ATS, automatic transfer switch. There's the UPS and 4 batteries, and so the UPS is what charges the batteries, and then the UPS takes the DC and creates AC and sends it through the automatic transfer switch when we lose power. Now there's also some battery heating mats and a surge protector. You need to heat the batteries to maintain their temperature to ensure they're efficient. Now out of that, then we go all the way over to the control cabinet. There's the 30 amp, and then it goes to all the distribution and all of the stuff that is required in that cabinet, to all the bus systems, right, that are connecting to the load switches for all of the lights in the system. So a fairly extensive electrical system that's required. Emergency vehicle sensors are one of the more common types of sensors that we see in the traffic intersection. The main purpose of the sensor is to provide a green light for emergency vehicles at any point in the traffic signal program. The sequence of interrupting the flow of traffic by giving preference to the emergency vehicles is called preemptive action, which is then abbreviated to EVP, Emergency Vehicle Preemptive. Although there have been different ways to accomplish this in the past, as in the recognition of a siren sound or strobe flash recognition, most modern systems use a specialized infrared sensor. Emergency vehicles are fitted with that particular type of infrared strobe light, which then triggers the sensor, causing the traffic control module to change the light sequence to give preference to the emergency vehicle in whatever direction they're approaching. The sensor tube is fixed to a collar on this particular brand, which can be rotated around the main housing. This is required as the sensor must point directly to the incoming lane of wherever an emergency vehicle may travel. And here's the infrared strobe on an emergency vehicle. The EVP strobes are mounted on all emergency vehicles for the region, and these lights can be adjusted for distance and frequency of flash. The EVP sensor is then set to trigger at the same frequency, making for less false triggers from any other type of infrared light which may be present on the roadway. Microwave sensors are another type, and microwave sensors are used to identify a vehicle moving in its detection pattern, then trigger the operation of a traffic controller. So here's an overhead view from an engineered drawing that's indicating microwave detectors, and they're showing here the broadcast range of where that sensor is supposed to pick up information of vehicle movement, and of course that would then be brought back to the traffic signal controller, and perhaps lighting sequences would then change. Radar sensors. Radar sensors are often deployed in regions where provincial laws permit the ticketing of vehicles for speed or running red lights without the use of law enforcement. These systems are then connected to a camera and flash, which is mounted on a pole. The camera takes a picture of the offending vehicle license plate if the radar detector determines its speed exceeds the limit. Other applications are simply to indicate approach speed for vehicles in high hazard locations. Radar sensors provide real-time speed for drivers. And here's an example of a radar sensor with a speed and red light camera. Traffic detection video cameras. Traffic detection cameras are used with specialized computer programs to identify, track, predict traffic within the visual scope of the camera. The information can be used by the traffic controller to adjust lighting signal timing. So here's just an excerpt from 2021. Richmond installed traffic cameras at 110 intersections. Now, some of the programs that they run the visual information through can look like this. Other times it can be more basic like this, where it's indicating how many vehicles are stopped and waiting, and it can then proactively adjust the timing of the lights. A very basic and very common type of sensor is called an inductive loop traffic sensor. Inductive loop sensors are extremely common. These sensors are simply loops of single conductor cable that are laid into slots cut into the roadway. Inductive loop sensors are typically installed at intersections to determine the presence and/or direction of vehicle movement. Inductive loop sensors are basically a large inductor with a core that changes with the overhead presence of a vehicle. The presence of a vehicle changes the henries of the inductor, which, when a voltage is applied, alters the current magnitude passing through. Cutting the proper dimension of slot is important, as well as the overlap diagonals in the corners. Depending on the area of the loop, the type of controller, and the type of vehicle to be detected, the number of wire loops may change. RWU90, single conductor copper conductor, is often used to build this sensor. It's really just a thick jacket RW90 conductor. The two ends of the single conductor sensor loop are brought to the edge of the roadway and up into a buried junction or splice box. At this point, the cable is then spliced to a standard multi-conductor cable, which is pulled into the traffic controller cabinet through underground conduits. And we can see here another engineered print, and we can see where they want the recessed or in roadway inductive loop sensors, and then they're brought over to the traffic controller through conduit. Traffic and pedestrian signals are highly regulated. This is to ensure that signals are easily identifiable in any region of the province or country. Although different manufacturers exist, they all will provide a very similar product that has been specified by the provincial standards. Here's just a cross-section of a number of different types, shapes, and sizes. And again, dimensions and overhang distances. Historically, traffic signals have been illuminated by incandescent light bulbs. These were a specific size and model which was able to operate for long durations of time before replacement. Below is an example of a Sylvania traffic signal light bulb. Lights required standardization as the color and brightness, had to be consistent for each intersection. Modern systems utilize LED lights to illuminate the signals. The color and brightness of an LED light is designed to visually replicate an older incandescent light. And so hopefully we don't see a whole lot of difference between them if we go in a city that has both incandescent and LED lights. Now, why hasn't the world switched to using color-changing light bulbs like LEDs instead of 3 separate ones on traffic signal lights? Well, the answer is an appreciable portion of the population has red-green color blindness. And, well, that kind of means if you couldn't see, then the difference between the colors, you would have no idea what, if you were to go or pause or what. So with someone with difficulty in discerning the difference, position is very, very important. So here in the UK, well, that's where the question came from, but really almost any country, Canada for sure, the red lamp is always at the top, green at the bottom, and then you have yellow in the middle. Multi-conductor non-metallic sheath cable or cab tire is typically used when wiring inside pole structures. The conductors are pulled into PVC or DB2 are standard single conductors. And so that would just be, for underground application. When we're pulling them inside the actual housing, it's got to be multi-conductor cable because it's got to go around edges and it's sort of rough and such. So it's got to be cab tire that's in here. Once you go into underground conduits, then you could pull single conductor cables or conductors as you would in any other electrical application. Here's an excerpt from the Electrical and Traffic Engineering Manual for British Columbia. There are lots of requirements around sizes of conductors, volt drop, and all sorts of stuff. On this one, voltage drop and load calculations. Allowable branch circuit voltage drop are as follows. So this is for the province of BC. Lighting circuits are not to exceed 4%. And then it says if there's no chance of expansion, then 5% is acceptable if approved. So all other circuits, including traffic controllers, post-mounted flasher, luminaires, all that, shall not exceed 3%. So a little bit more restrictive, perhaps, or a little bit different than what the Canadian Electrical Code indicates. Now, it's important to understand that all traffic signal and warning lights operate at 120 volts AC, and so all the wiring inside would need to be rated for 120 volt AC minimum. As technology advances, so does the sensors used, and so many sensors and cameras will utilize specialized shielded cable to reduce crosstalk and signal interference as they're pulled through conduits and inside the actual traffic signal poles and such, and so you can expect to use some pretty fancy cables in different applications. Generally speaking, all of the underground conductors that come in from all the different sensors and go out to all the different lighting standards or traffic signal standards at different sides of the intersection will all come up and terminate into distribution rails or wire binding rails here at the very bottom of the traffic controller. These are then wired up to all of the bus systems that we have for the load switches and the control relays and all of that stuff. It's important to understand that traffic signals are provincially regulated. Long ago, the province itself conducted the design, construction, and maintenance of traffic signal systems. Today, this is contracted out to different companies who specialize in this type of equipment. Much of the standards associated with traffic signal controls are provided in provincial documents specific to BC. So, Electrical and Traffic Engineering Manual is the prime go-to. Specialized training is available for traffic signal systems through different third-party training providers. There are generally 3 levels of certification for traffic signal installation, commissioning, and maintenance each. Each province has its own specific regulatory documents which indicate the norms of equipment and operation required.